Okay, so I'm Scott Gaudi. I'm a professor at Ohio State University. I also have a visiting position at JPL. I'll be actually visiting JPL for about 4 or 5 months, starting in August 1st for sabbatical. I'm going to be talking about WFIRST, K2, and how they relate to microlensing. I want to mention my collaborators, the Microfund collaboration, Andy Gould, Jennifer Yee, who you heard from yesterday, who introduced the topic quite nicely and has done a lot of the preliminary work for me. Kristen Clanton, who you also heard from yesterday. I'm not going to cover the stuff that he talked about. Kalen Henderson, I need to point out specifically because I've stolen some slides wholesale from him, but he said it was okay. And Matthew Penny, who's really done all of the heavy lifting when it comes to WFIRST, which the yields, which I'll be talking about, and of course the WFIRST science definition teams and microlensing science investigation team. Okay, so we've all seen many versions of this plot. This is a somewhat outdated version. Of course, this is the canonical exoplanet demographics plot. This is just planet mass on this axis and Earth masses. This is planet separation and semi-major axis. These are the various planets that have been discovered with measured masses. It's a little outdated. The reason why you don't see the big cloud of points here in Kepler is both because it's outdated and also because I've only included things that have actual measured masses. And these points are color-coded by the discovery technique. And so, as we know, we have lots of confirmed planets. I think this includes the Morton update, nearly 3,000 confirmed planets, mostly from Kepler. We have a total of 5,400 roughly candidates plus confirmed planets. And of course, of that, there's a very small subset that are actually due to microlensing, only about 50. And so what I'm going to try to explain to you or try to convince you of is that that is going to change very rapidly. And soon microlensing will be the premier method of finding planets in a statistical sense in the same way Kepler is today. Okay, so what I'm going to basically try to convince you is that microlensing is currently reaching a watershed. Hopefully you got some sense of this from John Yee's talk. What do I mean by watershed? Well, there's 2 different definitions. Of course, I don't really mean this one. What I mean is this one, an event or period marking a turning point in the course of action or stating affairs. So the microlensing field is reaching a turning point or has reached a turning point which I think is very exciting and which will basically amplify the field exponentially. Okay, so where does this watershed come from ultimately? Well, it comes from the 2010 Decadal Survey. So the number one recommendation for a large space mission in the 2010 Decadal Survey was WFIRST. And contrary to what you may have heard, WFIRST is not and never was a dark energy mission. It had 3 primary goals. One of them was dark energy, of course, with supernova, baryon acoustic oscillations, and weak lensing. But the other equally important science goals were a microlensing survey towards the bulge, and then a general astrophysics program, including a galactic plane survey. So that endorsement by the Decadal Survey really launched microlensing from sort of a backwater poor cousin detection method that most people could ignore, and put the talks on the last day, like today, to a method that actually people will have to start to pay attention to. So as a result of this watershed, there's been a fair amount of fallout, and you heard some of this from Jen Yee, so I won't cover that. She talked about Spitzer. So we've gotten a lot of time on Spitzer to do microlensing parallaxes, which allows us to get masses and distances to the microlensing stars, mass function and galactic distribution of planets. There's also the K2 campaign 9, which I'll talk a little about. There's campaign 11. These will also do microlensing, and we'll do both of these, but we'll also try to validate free-floating planet masses. I'll talk more about that. There's a new ground-based survey coming online called KMTNet, which is 3 1.6 meter telescopes, 4 square degree fields of view. This is expected to quintuple the detection rate roughly per year. I won't have time to talk about that, unfortunately. And then I'll talk about WFIRST, which is really going to transform this field from sort of a trickle of events detections to detections en masse, very similar to Kepler. Okay, so K2. What is K2? Campaign 9. So K2 Campaign 9 is actually the 9th campaign of the K2 survey, and it is pointing at the galactic bulge. So they actually had to turn the spacecraft around in the opposite direction that it was normally going in order to have it be facing visible, the bulge be visible at the same time that it's visible from the ground. And right before they were about to do that, the spacecraft went into emergency mode or whatever. But we were told that this was not microlensing's fault. But there's some part of us that still thinks that maybe the spacecraft knew that it was about to do microlensing, so it decided it was going to try to shut down. But nevertheless, doing a lot of hard work with the K2 team, who we really have to thank. They were able to get it back and going with a relatively short amount of downtime. So what is K2 Campaign 9? Okay, so here's the full stamp. This doesn't show up very well. Microlensing is just looking at, for microlensing, we are looking at we get most of the pixels, but rather than targeting specific stars, because we don't know when microlensing events are going to occur, we just targeted a large, what we call super stamp, a region of where we expect the highest event rate as predicted by Radek Polsky. And you can see a summary of the K2 Campaign 9 expectations in a paper by Kalen Henderson. Again, I've stolen most of these slides from him. So the total area is about 4 square degrees. The cadence is 30 minutes. We expect about 100 events, total microlensing events. And so it started in 22nd of April. The duration was slightly less than a full campaign because of this emergency mode. But nevertheless, still substantial. And so the idea is that we look for microlensing events that we can see both from the ground and from K2. And so, I don't know if I can, no. So the idea, which I think Jen explained, is that what we want to do is get microlensing parallax. So generally, microlensing, you only measure the time scale of the event. That's a degenerate combination of the mass, distance, and proper motion of the lens. And so if you really want to measure the mass, you have to break that to degeneracy. You need extra information. And one way you can do that is by looking at the microlensing event from two relatively largely spaced observatories, for example, the Earth and Kepler and even Spitzer. And if you do that, the microlensing event is going to look different from the ground and from the space. And that difference is proportional to the Einstein ring of the planet or the microlensing event projected onto your source plane or your observer plane. And so that means that you're better able to estimate the masses. And in particular, you can try to validate free-floating planets. So these are the 3 main science goals of Kepler-2 Campaign 9. I'm not going to talk about the other 2. I think Jen talked about the galactic distribution. I'm going to focus on the free-floating planets. So one of the main motivations for doing this is this very intriguing result from the MOA and OGLE collaborations that's quite old now, where if you look at the timescale distribution from 2 years of MOA data, you see that it has this basically log normal distribution, which you can explain more or less from things you expect, stars, brown dwarfs, and remnants. But there's this shoulder of about 10 events that is larger than what you would expect based on this analytic fall off that you predict. And so they interpreted these excessive short time scale events as due to either wide or free floating, widely bound or free floating planets. And in fact, they argue based on direct imaging surveys that these are likely to be due to free floating planets. And I think Christian talked a little bit about his work on this ongoing right now. But the very interesting thing about this result is that it implies that there's roughly 2 free-floating Jupiter mass planets per star. And this result is very hard to understand basically in any formation scenario that you can imagine. And it's a much larger reservoir than we see anywhere else in terms of bound planets or even planets in young open clusters. So this is a result we'd really like to test if it's true, but the problem is all we measure is the time scale. So these could be due to free-floating planets, or they could be due to stars that are just moving very fast. But despite the fact that those two scenarios will give you the same time scale, they'll give you very different parallaxes because the Einstein ring of the planet is much smaller than the Einstein ring of a star. And so when you project it back on your plane, the difference when you look from Kepler or Spitzer and the Earth for a planet will be large. In fact, you may not even see the planetary signal at all, or the short time scale event at all. But if it's due to a star, the difference will be very small. And so you can distinguish between those. And so that's one of the main goals. So in order to do this, you need not only Kepler, but you also need a host of ground-based observatories. And so due to a lot of work from Kalin and Yossi Schwarzfield and Matthew Penny and Rachel Street and many other people, they marshaled an enormous number of resources to follow the K2 K2 Campaign 9 superstamp during the campaign. So the weather was actually notoriously bad this year in Chile. So unfortunately, we didn't get quite as much data as we wanted. But nevertheless, this was probably the most intensely monitored area of the sky, at least for the duration of the 70-day campaign ever. There's lots of data. And so what we hope to do is be able to look for microlensing events in Kepler and also in the ground, and see if we can see a difference in their properties due to the microlensing parallax. And so one survey that's going to help with this is this KMTNet that I mentioned. And this is the sort of, these are the survey fields of KMTNet. The ones here in black are the ones that are surveyed most rapidly. And you can see that the K2 superstamp falls right in there. They're surveyed every 15 minutes. So this will be an important survey for looking for planets in Kepler and the Earth. And so we expect roughly 7 free-floating planet candidates. Again, I get our candidates because we don't know if these short timescale events are actually due to free-floating planets or not. That's what we're going to try to test. And we'll find a total of 100 events. And this is probably a lower limit because we'll probably find events in the K2 data that we will not find in the ground-based data. Okay, so that's a K2. On to Kepler. How much time do I have? Okay. Now I'm going to go on to WFIRST. So the main goal of WFIRST is to complete the statistical census of planets. So why would we want to do this when we already have Kepler? Haven't we learned everything we know about the demographics of planets from Kepler? The answer is basically no. You can see that partially here in this plot, which I just showed before. And the main point of this is that the positions of the planets that we know of are more or less disjoint from the planets in our solar system. And there's this vast white area here, which is not devoid of planets, we don't think. It just hasn't been explored because none of the methods that we've developed so far are sensitive to planets in this region. So you know, obviously Kepler has been great. It is the first real demographic mission with very large numbers of planets. We've learned an enormous amount about planets, a lot of surprises from Kepler. It's been fantastic, but it is not the whole story, okay? And so just to bring that point home, some of you have heard me say this before, but it's pretty striking if you haven't. If every single solar system had an architecture like ours, Kepler would have basically found no planets to within 95% confidence, okay? Because it's simply not sensitive to any of the planets in our solar system, even the Earth and Venus, barely. So maybe they would have found 3 if they were lucky, and maybe they will find 3 Earth analogs. We hope so, because that will enable us to estimate A to Earth. But all of these planets are more or less disjoint from the planets in our solar system. That's the main point. Another way to bring that home is this somewhat unfair plot showing a plan view of our solar system, and there's Kepler's search area right there. So just to give you a sense of scale, of course, so it gets out to the Earth and maybe a little bit to Mars for bigger planets, but really this entire region out here is completely insensitive to. Okay, so why would we want to complete the census? Well, I can give you a lot of theoretical reasons. We still think that most giant planets form beyond the snow line, so it might be nice to know what's out there. We'd like to place our solar system in context. There's this weird paradox that the planets that you form in the habitable zone are likely to be formed out of materials that have no water. So that means that the water, to make them habitable, has to be delivered from beyond the snow line. So we'd like to know what's out there. And we'd just like to understand the frequency of planet formation in different environments, like the galactic bulge, which microlensing is sensitive to, which very well might have a different planet frequency because of a different formation history. So those are all, good theoretical reasons, but any good exoplanet observer knows that they shouldn't rely on theoretical reasons to justify their surveys. The real reason why we want to do this is this, of course. This is 51 Peg, the first discovery, well, depending on who you ask, the first discovery of a planet orbiting a normal star, one that was completely unexpected and basically set the tone for the field for the last 20 years, which is basically whenever we look in some new region of parameter space, we find something we didn't expect. So that's the real reason to look. Basically, Mother Nature is much more imaginative than we are. And we should keep that, we should respect that, and we should complete the census. If we really want to complete the census, we want to get down to Earth masses and below. In order to do that, these are the basic requirements. You have to monitor hundreds of millions of bulge stars continuously on a time scale of 10 minutes, relative photometry of a few percent. You have to resolve main sequence stars, and then if you really want to measure masses, you have to resolve the background stars for primary mass measurements, which requires a resolution of roughly 0.1 arcseconds. So all of this leads you to basically to space, which was first pointed out by Dave Bennett and Sun Rhee in 2002. The basic reason you can see here, this is a ground-based image from VVV at an excellent site, Chile. This is 1 arc minute by 1 arc minute of the bulge for basically 5 arcseconds by 5 arcseconds. And here's an equivalent simulation of a field with WFIRST in the same region. And so everything here you think might be a star, you can see is actually a collection of many stars. And so that means that you have lots of systematics. Going to space allows you to go to the infrared. You can go to more extincted fields, smaller sources. You get better resolution. You get more complete coverage. And you get better control of systematics. And all of this enables a whole host of science that you can't achieve from the ground. Okay, so that's where WFIRST comes in. What is WFIRST? Well, I think we basically all know this. I can go through this pretty quickly. Again, it's the #1 recommendation for a large space mission of the 2010 Decadal Survey. It was a combination of 3 missions that were proposed separately, all of which had very similar architectures and hardware. And it was designed to do these 3 science goals, as I mentioned. Now, the WFIRST has gone through a lot of machinations and iterations. I've been through all of them since 2010. We came up with a couple reference missions. But the real turning point of WFIRST was, of course, when NASA announced that it had been donated 2.4 meter space qualified telescopes from the National Reconnaissance Office. Of course, we aren't supposed to know what these telescopes were originally built for. We all know what they were originally built for. In fact, NASA was told that the only thing they cannot do with these telescopes is point them at the Earth. Anyway, this enables much better science, but it also enables you to allow you to put on a coronagraph, as Carl talked about. So that's a very exciting possibility in a way of achieving the medium large space recommendation of the Decadal Survey and actually producing science. So is WFIRST real? Yes. Congress keeps giving NASA more money than they ask to support WFIRST. That's good. We had a new start in February 18th of this year, and science investigation teams were proposed in October last year and selected in December 2015. So we are now in the process of setting requirements and developing the mission, et cetera, all that boring stuff. All right, what about the interesting stuff? I won't go through this. This is basically, you can look this up. It's basically Hubble with 200 times the field of view in terms of the wide field detector plus a coronagraph. So what do you expect from microlensing? So the simulations have been done by Matthew Penny. He just did a notional 10 fields near the galactic center. He simulates stars. He puts microlensing events in them, and then he puts planets in those microlensing events, and then he sees if he can detect planets. So now we're actually getting into detections, which I guess was the theme of this meeting. Okay, so here are two simulated detections from WFIRST. This is something which is twice the mass of the moon, or roughly the mass of Ganymede. This is a 27 sigma detection. And this is a free-floating Mars mass planet. This is a 23 sigma detection. So when you ask the question, is there a planet in our data? This question is a lot easier to answer in WFIRST and microlensing in general, because the signals that we're looking for are not 1 part in 10,000. They are 1 part in 10 or 1 part in 100. And so in general, false positives, noise are not an issue. I'll say a little bit more about that in a second. So what do you expect? So there's Kepler search area again. Here's WFIRST search area, basically completing the census. Now this is not exactly fair, as I mentioned. This is a more fair comparison. I call this the Penny plot. It's made by Matthew Penny. This is mass and Earth masses, semi-major axis. This is the region of sensitivity of Kepler, or would have been if it had the extended 6.5-year mission. These are, I think, a non-updated subset of the Kepler discoveries. And then these is the region of sensitivity of WFIRST, where you would expect 1 planet. If you had 1 planet per star, you'd expect 1 detection. And you can see we're sensitive to all the planets in the solar system except for Mercury, and we're even sensitive to planets with a mass of roughly twice that of the mass of the moon, either bound to their parent stars or just orbiting by themselves. These blue dots are simulations of what we'd expect to detect. Don't believe them. They're not, they're just made up. Of course, that's why we're doing the survey. But the main point to take away is that the number of red dots here is roughly equal to the number of blue dots. In other words, this survey is going to have a roughly equal number of detections we expect as Kepler. And it will also, of course, open up this broad new region of parameter space. So what do we expect to find? Roughly 3,000 cold-bound exoplanets. 300 of those should have the mass of the Earth. 40 of them should have the mass of Mars or smaller. And then we expect roughly 40 free-floating Earth mass planet detections if there's 1 such Earth mass planet per star, which is probably conservative. I want to note that all of these predictions are based on a chi-squared threshold of 160. So that's 12 sigma. This is quite a bit higher than is required by any kind of Gaussian white noise that you might expect. Okay, so that'll be, I'll talk a little bit about that in a second. Okay, so on to the theme of this conference. Because our signals are so high, I kind of question why I was asked to give a talk. We don't have to deal with a lot of the issues that the people on the cutting edge of radial velocity and transit surveys have to deal with. But maybe we will have to deal with them in the future. So I like to think of this, and I apologize if I'm going over material that has been gone over many times. I just arrived last night at 2 o'clock in the morning, so I haven't been here for most of the conference. But anyway, there's 2 issues in terms of answering the question, is there a planet in our data? One is that, is there a signal consistent that is above that, consistent with noise, either white or not, typically not. Generally, this has not been an issue for microlensing because we've employed signal-to-noise thresholds like a delta chi-squared of 300 that are much larger than any random noise fluctuations, even considering correlated red noise. I'll show you why that's an okay thing to do for microlensing in a second. For a lot of surveys, that would be catastrophic. You'd basically be eliminating all of your detections. Microlensing doesn't have that issue. Of course, the second question is, okay, I see a signal, I believe it's a signal, is it actually due to a planet? So astrophysical false positives have generally not been a concern because the things we're looking at are things that have deviations of a few percent to tens of percent around with source stars that are roughly solar-like stars. And we know that solar-like stars just don't vary like that on those kinds of timescales. There are things like flares, which are something we do have to worry about, but those flares do not really look like microlensing events at all. And also, the other thing is that we tend to look out for little dips or blips on top of other microlensing events. And so the probability that you would get some random variation in the stellar brightness right when you're getting a microlensing event is pretty low. So we generally have not had to worry about false positives in terms of astrophysical false positives. Something that has been more of a concern for us have been degeneracies. So Jen talked a lot about this timescale degeneracy, but there are other degeneracies in the sense that there are various models that can equally well fit the data, and I'll say a little bit about that. However, I think once we get to K2 and for sure, and WFIRST maybe, this may be more of an issue. So maybe I should have given this talk 10 years from now. But maybe the smart people in this room who are thinking about how to dig very weak signals out of noisy data can help us actually get a lot more out of WFIRST than we're naively thinking right now. And that's my main reason for giving this talk. So K2 is one big problem. How much time do I have? 8 minutes, okay. So K2 is one place where things are going to start to get difficult for microlensing. So this is the full frame image of the Campaign 9. It's beautiful. See dust lanes, Lagoon Nebula. See these large regions of many stars. This is where our microlensing event rate is high, and where our super stamp is. So this is a field in the galactic bulge, and I think taken with, I can't remember, HST. But anyway, if you look at the size of a Kepler pixel, these are the number of stars that you get in a pixel. So this is not photometry of one star at a time. This is trying to extract photometry of, say, this star being microlensed when it's being blended by all of these stars. And of course, we all know the K2 systematics are present as well. And so what we have is we have a target star with a light that's in a pixel with a light curve that looks like this, and then we have a bunch of reference pixels that do similar kinds of things, and we want to try to take these deviations due to the motion of the spacecraft out. So the way that this is being done is that we have a causal pixel model. So we take a bunch of input pixels, we put in a microlensing event, and we fit it and maximize the likelihood of the fit to that. And there's lots of free parameters, like the number of pixels or the number of different parameters. But this is basically the kind of method that the NYU group uses. And in fact, this method is being perfected by Dun Wang at NYU. So here's your microlensing event. Mostly it's just systematics, but there's that little peak. This is your reference thing that is, you hope is just systematics. You take these and subtract them, and what you're left with is a beautiful microlensing event. The problem is that again, with all these free parameters, it's hard to know how to optimize these things. And unlike transit signals, when you try to do this as best you can end up actually removing or even creating microlensing events in your data. So this is someplace where we're really starting to have the same challenges that people are having with radial velocity and transits. Okay, so that's TBD. We think Dun's pretty smart, so we think he's gonna solve this for us, but we're working on it. Okay, what about WFIRST? Okay, so I told you that it doesn't really matter very much about where we do our selection threshold, so we're free to choose pretty high detection thresholds. And the reason for that is that the distribution of chi-squareds of signals of microlensing events is exceptionally broad. It's not like a transit event where basically once you get to a signal to noise that's larger than some value, you just don't detect the transit at all. Here there are signals that range from hundreds of percent to a few percent. Okay, and so that gives you this very relatively shallow distribution of chi-squared. And this is from a simulation by Kalen Henderson of the KMT-net. And so you can slide things along here pretty far without changing the number of detections all that much. And that's both good and bad. This is a similar plot for WFIRST. Here the lines are even less steep. You can see they're steeper for lower mass planets, as you might expect. Eventually, you get a fall off because of the finite size of the source. But you can see for factors of 4 in detection thresholds, the number of events you expect is relatively low. And so that's good because that means we're fairly robust to systematic errors, and we can impose very high detection thresholds if we want. But what if we don't want to? What if we want to actually take advantage of all the statistical power of this data? Then we want to move down into here. And so then what problems are we going to start to face? Well, again, we're going to start to face the same problems when our signals become of order our noise, and then we have to figure out how to disentangle them. So just very quickly, how planetary perturbations work. You basically have caustics. When the source crosses the caustic, you get a deviation. There's several different kinds of caustics. I'm sort of running out of time, so I won't go through this. But the main point I want to make is that if you cross this caustic here, that's what located due to the planet, you get very large signals. These are probably not anything that we have to worry about in terms of systematic errors. But if you cross this other caustic due to a planet's inside the Einstein ring, you can get relatively subtle signals. And here we might have to worry about systematic errors quite a bit. There's other issues like degeneracies. So there are models which have very different parameters that can explain the data almost equally well. This is due to a mathematical degeneracy in the lens equation itself. And so one of the best well-known is the close-wide degeneracy for high magnification events, where you can see an event that has a separation from the Einstein ring of D, and one that has a separation of 1 over D produces perturbations that are almost identical. Now with WFIRST, if we can control our systematics to the millimagnitude level or better, then we can break these degeneracies because these two caustics and these two signatures are subtly different at a relatively low level. So that's one thing we have to figure out if we can do. The other thing is that if you, I'll skip that one. If you, you can also get similar sorts of deviations from things that are not even planets that are due to binaries. And again, if your photometric precision is poor, then it's going to be difficult to disentangle them, and we've had that issue before. But if it's relatively high, then we can disentangle them better. And so again, with WFIRST, the goal will be try to dig in as much into the noise to try to break these degeneracies in our data. Okay, and then finally, two sort of related issues is that if we can really dig into the noise, we have a much higher probability of detecting multiple planet events. So here's an example from a paper, the original paper by Bennett and Ree, showing 2 multiple planet events. One is a Jupiter and a Saturn. Here's a signal from the Jupiter. That's pretty obvious. But here's a signal from the Saturn, which is basically this vague shoulder on top of your microlensing event, which could easily, you can imagine, be mimicked by systematics. So if we want to really get lots of multiple planet events, like Jupiter and Saturn, we're going to really have to figure out how to control our systematic errors at this level. Here's a similar case, but now here we have the Earth mass deviation, also dead obvious. But then here's the Jupiter mass deviation. Again, it's just this vague shoulder. And then so there's a question of not only whether or not we can detect these signals, but can we actually distinguish between a Jupiter and a Saturn in these kinds of data? So not only can we say that there's a real signal there, but can we actually figure out the parameters of the planet? This is something that we do not know and depends quite strongly, I think, on what our final photometric precision with WFIRST will be, which we don't really understand yet. And here's another example of where high photometric precision may bias a lot. Here is a detection of a Earth mass, yes, Earth mass, actually a little bit less than Earth mass planet from not WFIRST, but something similar to WFIRST. Space-based microlensing survey. You can see this is not a subtle detection, but you can see there's this little extra blip right here, and if you blow that up, this is what the blue line is what you would get if you just had the Earth mass planet. This little extra blip is what you get if this Earth mass planet happens to have something that's roughly 3 times the mass of the moon. Okay, so if we can get down to this very low systematic errors, and these are not very small numbers, these differences, but they're but you can again imagine that systematic errors may cause problems and create glitches like this. But if we can manage to control them, then we can hope to detect actually moons like our moon of terrestrial planets. Okay, all right, so I've tried to do two things here. One is to just summarize K2 and WFIRST, but also try to put it in the context of the goals of this conference in terms of is there a planet in our data, and so as far as the review of WFIRST and K2, most of this is online and you can find it. But what I'd like to encourage the audience here to think about, if not today or if not 2 years from now, at least starting maybe 5 or 6 years from now, is how do you apply the methods that you're now using to try to extract very low signal to noise signals from radial velocity and transit and other data. How can we start to apply those techniques to things like WFIRST and maybe even K2 so that we can maximize the science yield from these missions? Thanks.
Is there a planet in that likelihood?
Right. So I think the question is, what is the role of precursor, contemporaneous, and what was the other one? Follow-up observations in WFIRST. I think all of them can play a very large role. In terms of precursor observations, there are two main things that I think we would like to have. One is a much better and a much deeper luminosity function of the fields that we might think or we might observe so that we can maximize our event rate. Another is an infrared survey from the ground so that we can get experience from infrared microlensing surveys, which we've basically to zeroth order never done before, and WFIRST is expected to be in the infrared. Also to figure out what the event rates might be in the more extincted fields that we might monitor. In terms of contemporaneous observations, I think, WFIRST will be at L2. If we can monitor these fields from the ground, then we have a baseline of basically 0.01 AU, which is small compared to the Einstein ring of a star projected onto the Europlane, but is roughly the size of a planetary Einstein ring projected onto Europlane, at least for an Earth-mass planet. And so that means that we can start to break degeneracies from contemporaneous observations from the ground in space. And then the other thing you can hope to do is that with sort of maybe next generation 30-meter telescopes and adaptive optics, you can actually go and follow up microlensing events found from WFIRST, look and watch as the source and lens separate from each other, which also allows you to break degeneracies as well and measure the microlensing parameters as well. So that is sort of, all of those deal mostly with the time scale degeneracy. In terms of the degeneracy between the models, I'd have to think a little bit more carefully about that, but we do have a fixed sampling in WFIRST, and if we can get a higher sampling from the ground and the events are visible, then we might be able to distinguish between models better by more. So that would enable us to get properties of the source stars, which could be interesting both for galactic structure and also for helping us understand the properties of the angular size of the source star. I think I would put that down a little bit lower on the list, but it could be useful, yeah. So this part of this question is part of the answer to this question is the question that I'm throwing out to you, which is something that we have to figure out, is how deeply can we dig into our noise. So being conservative, with a chi-squared threshold of something like 500, we think we can find things that are roughly twice the mass of the moon or the mass of Ganymede and a free-floating planet. But if we are able to control our systematics better and can get down to and really trust millimagnitude deviations or even smaller, we might be able to get down to even lower masses. I'm not going to throw out a number there, but even lower than the mass of the moon, perhaps.
In WFIRST, is the microlensing sharing, is it observing at the same time as the dark energy, or you have dedicated time?
No, we have dedicated time. So there's 7. So the question is, are we sharing time with the dark energy survey during the microlensing survey with WFIRST? The answer is no. We have only certain windows when we can look at the galactic bulge due to sun pointing constraints, and those are just like 72 days. And we have 2 seasons a year. We're going to hope to do, I think, 7 total seasons for 432 days. But during those seasons, we will not be interrupted. And we're fairly sure we won't be interrupted. This is still being negotiated somewhat in case some supernova goes off or something. We might be able to be, but in general, we have that time dedicated for those seasons when we can actually look at the galactic bulge.
For Kepler and finding planets, the main source of false positives is ecliptic binaries.
Yeah.
For WFIRST, what's going to be the major source of false positives?
Astrophysical false positives. At the kind of thresholds that we're thinking about, I don't think there are any.
False positives, you mean false alarms,
Oh well, so my point at the thresholds we're thinking of now, we don't think that stars vary with the kinds of properties that you see with vary like microlensing events. But if we really want to start digging down deep into the noise, then there might be things that we haven't experienced yet. Now, the results from Kepler seem to indicate that even at the millimagnitude level, most stars are pretty quiet. But you know, we just don't know. So I would say that to do our basic result, we're not worried about astrophysical false positives. But if we start to really try to push down much deeper into the noise, then things might be important. Things like flares, there are these kinds of stars called bumpers. They roughly can mimic microlensing events, but in detail, they don't look like microlensing events at all. I mean, most of these perturbations, as you can see, are pretty characteristic. They don't really have anything that we haven't found any astrophysical source other than microlensing that produces a one-time deviation with these kinds of characteristics.
Can you elaborate a bit on how Gaudi helped you? Can Gaia help you? Gaia helps everyone.
Gaia is good for everyone. I love Gaia. Unfortunately, Gaia will not help us very much with understanding. So one of the things we would really like to know is the properties of the galactic bulge. So amazingly enough, we don't really understand the galactic bulge well enough to produce realistic event rates and therefore really figure out where we want to point. We would love it if Gaia could do that for us. Unfortunately, Gaia does not do very well in the galactic bulge. Now, it will do well in sort of mapping out the galactic disk, and that will help. But I think where Gaia might help is that Gaia will be able to do astrometric microlensing of some fraction of microlensing events. And then that will teach us, well, A, we'll learn a lot of science like that, like the number of free-floating black holes, perhaps. But also we'll learn about astrometric microlensing, which is something that we've never done before successfully. And so that's where I think Gaia might help microlensing the most.